All right, math counts. Here we go. We've got workout 2 from the 2026 problem set. This one's brutal. I'm not going to lie. This might be kind of a long video. Usually, like the workouts, workouts and warm-ups, they get harder and harder as you go. This one just like jumps it up to like an 11, like right away. So this one might take a while because this one took me a while to complete on my own. So here we go. The letters in the word mathlete are arranged in a random order. What's the probability that no two consecutive letters are the same? Express your answer as a common fraction. All right. So we've got the word mathlete. And what we notice in that word is it even a word? I'm not sure. But anyways, we notice that there's an M, an A T. Well, there's two T's and there's two E's. So we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 different letters. So there are 8 factorial ways to arrange all those letters, but there's 2 T's. So we would divide out 2 factorial to show that the 2 T's can be done either way, backwards or forwards. And then there's also 2 E's. So we would divide out those to show that the 2 E's, backwards, forwards are the same. So this would represent all of our possibilities. This is our denominator, basically. This is all the different ways that you could rearrange mathlete. Okay, so basically on top we've got 8 times 7 times 6 times 5 times 4 times 3 times 2. And on the bottom we've got 2 times 2, 2 factorial and 2 factorial. So these 2's cancel out this 4. So basically, our denominator is 8 times 7 times 6 times 5 times 3 times 2. That comes out to, if you're using your calculator, to 10,080. All right, so that's our denominator, 10,080. Now we have to find out what our numerator is. Okay, we don't want to have 2 consecutive letters that are the same. Now we're going to deal with these individually. What if I had the T's next to each other? So we don't want the T's next to each other, but what we can do is, let's see, we've got an M and an A, and then the T's we'll just put together, we're going to just like put them together like they're one group. So we don't want this to happen, to have a group of these 2 T's. And then we'd have an H and an L and an E and then another E because I've already got the T's. So 1, 2, 3, 4, 5, 6, 7. So we've got 7 things there. So we don't want this to happen. So we're going to want to remove them from the possibilities. So there are 7 factorial ways that we can do that because we're pretending that this double T is just one thing moving around together. But then we also have these 2 E's over here that are the same, so we're going to divide this out. So basically this is 7 times 6 times 5 times 4 times 3 times 2, and then divided by 2. So there are 7 factorial divided by 2 ways where these 2 T's are next to each other, which is what we don't want to happen. So canceling this out, we end up with, I used my calculator earlier, it's 2,520. All right, so of the 10,080 combinations where we can, move around the letters in mathlete, we don't want to use 2,520 of them because that's when we would have these 2 T's together. Now the exact same thing, the exact same process can be done with the double E's. We can group them together, then we'd have 7 factorial over 2 factorial because we have these 2 T's as well. So this is for the T's, and then I would subtract out this for the E's, the double E's. So this is double T's. This is how many combinations have double T's next to each other. This is how many combinations have double E's next to each other. Now you really have to think through this process, and hopefully you've noticed what's happening here is sometimes with the double T's, we would have double E's. So the last thing that we have to do is add back in the combinations where we're double counting, because some of these double T's have double E's and some of these double E's have double T's. Oh, I told you it was brutal. So what we now need to do is, okay, we've got M-A double T H-L double E, where the double T's and double E's are both the same. So we want to know how many of these combinations we have double E's and double T's, and what we want to do is add them back in, because inside of here, we're double counting. When we have double E's, it's possible to have double T's. You know what I'm saying. It's early in the morning. It's hard to talk. Anyways, we've got 1, 2, 3, 4, 5, 6. That's 6 factorial. There's no doubles to go at, because remember, we're counting these as just one thing. They're kind of like connected to each other. So 6 factorial, 6 times 5 times 4 times 3 times 2 ends up being 720. So total combinations, take out the combinations where the T's are next to each other, take out the combinations where the E's are next to each other, and then add back in the combinations where we have double T's and double E's, because we have double counted them inside of here. And all of that comes out to 5,760. 5760. Whew. And now it wants it as a fraction. So here's what I would suggest. Know how to use your calculator. So this is a calculator problem. So if I do 5760 divided by 10080, I get this number, but they want, oops, you can't see it, reflection. So I get this number, but we want it as a fraction. But these types of calculators, the TI-30XS, we can use this button down here, and if we have a rational number that can be turned into a fraction, it'll turn it into the fraction for us. So we can hit this button down here, and now it has turned it into our fraction of 4/7. So knowing how to use your calculator will save you some time. This reduces to 4/7, and that is your answer, 4/7. There's got to be an easier way to do that. I just haven't figured it out yet. All right, next one. Consider a 5-term arithmetic sequence that starts with 6 and increases by 5 with each term. Okay, so we got a 5-term sequence. Oh, I'll read it and then go over this. Sorry. Another sequence is added to the first term by term, resulting in the sequence 25, 25, 25, 25, 25. What is the absolute difference between the first and last term of the second sequence? All right, so we've got the first term. First sequence has 6 terms. It's starting at 6, and it's increasing by 5. So 11, 16, 21, 26. So we've got an arithmetic sequence. That means we're adding the same amount each time. We're starting with 6. So this is the first arithmetic sequence. The second arithmetic sequence, they said that they're going to add it to the previous one so that we get 25 each time. Now, I'm only doing the first and the last because that's the only part of the sequence that we care about, because we want the absolute difference between the first and last term of the second sequence. This is our second sequence. This is what we're adding to the first sequence to get 25 every single time. So 6 plus what equals 25? 6 plus 19 is 25. 26 plus what is 25? 26 plus -1 is 25. So what's the absolute difference between 19 and -1? So to go from 19 to -1, that's a distance of 20. So our answer should be 20. Not too bad. Just that first one was brutal. All right, what is the sum of the first 10 integers that have 3 distinct digits? All right, so 3 distinct digits. So I will go with the smallest number first. 1, 0. I can't do 0 because we want 3 distinct digits. I can't do 1 because then I'd have the ones. So my first distinct combination would be 102. Okay, then 103. then 104, then 105, 1, 2, 3, 4, then 106. All right, there's the first 5. Distinct means we can't repeat any of the numbers. So 102 was the first one with no repeated numbers. Okay, I need 10 of these. So here's the first 5. 107 would be the next one. 108 would be the next one. 109 would be the next one. All right, and now I'm at 110. That doesn't work. None of the teens of the 100s are going to work. So my next number that might work is 1, 2, 0. None of those are the same. Remember 111, 112, 113, all those had double ones, so we can't use those, so we would jump to the 120s. And then after that, the next number won't be 121. That doesn't work. 122 doesn't work. 123 would be the next one. So there's the first 10 integers that have 3 distinct digits, and I want the sum of them. So we would use our calculator at this point, add all that up, and we get 1,087. Next, a square is inscribed in a circle with a radius of 6 centimeters, shown at right. What is the length of a side? What is the length of a side of the square? Express your answer as a decimal to the nearest tenth. All right, so I've got a square here. And it's inside of a circle. So this is a radius of the circle. This is 6. All right, so a lot of different ways you can do it. You can use area, because the diagonals, if you multiply the diagonals and then divide by 2, that would give you the area. You can do that. I prefer to do this. I would go straight down here. This would be 90 degrees. Since this is a square, this radius would bisect this 90-degree angle. Seriously? My lights went out. I wasn't moving enough. So we would get 45 degrees here and 45 degrees here. All right. Probably shouldn't have drawn that bigger. My bad. Anyways, here's what we got. We've got a right angle. This is 45 degrees because this radius is bisecting this angle here. We have this side is 6. Now we just need 2 of these. Well, this is one of our special right triangles. In a special right triangle, the pattern is this side and this side are the same because it's isosceles. And then this side would be a square root of 2. So if a square root of 2 is 6, then we can do a root 2 equals 6, divide by root 2, and get a equals 6 divided by root 2. And then for this one, we want to double this amount because this is a and this is a. So the fastest way to do this at this point was just take out your calculator and double this amount right here. So this would be, if I double this, this would be 2 times 6 over root 2, which is 12 over root 2. So let's pull out our calculator and do 12 divided by root 2. 12 divided by the square root of 2 ends up giving us a syntax error. Why? Oh, because of how I typed it. Square root, arrow over, there we go, now it's going to like me. Okay, it's giving me an answer as a reduced fraction because I have it in MathCounts right now, so I'm going to hit this side-to-side button, and now it's going to give me the decimal approximation, so our answer is approximately 8.5. All right, there are a couple other ways that you might have done this problem. Let's say that you didn't know the pattern here for a root 2. You could have just used the Pythagorean theorem if you know that these are both a's. You could have done a squared plus a squared equals 6 because Pythagorean theorem, it's isosceles. So you would have had 2a squared equals 6. Then you could have divided, oh, sorry, equals 6 squared, my bad. Oops. So we got 2a squared is equal to 36. Okay, then we could have divided by 2. A squared equals 36 over 2. And then taken the square root. So a would have been the square root of 36 over the square root of 2, which is 6 over root 2 that we got over here. So if you don't know your patterns for your special right triangles, you can still use the Pythagorean theorem over here to work that one out. All right, let's move on. This one's going to be long enough as it is. All right, next one, number 155. Okay, an even number n has 16 integer divisors. If one of the divisors is chosen at random, the probability that it is even is 3/4. What is the least possible value of n? Okay, so I've got a number n. It's got 16 divisors, and 3/4 of them are even. Okay, so thing about divisors is if I have an even number of divisors, then my number is not a perfect square. The other thing about divisors is, remember, like if you break down a number, let's just break down an easy one. Let's do 18. If I break down 18, 18 is 2 times 9, 9 is 3 times 3. So the prime factorization of 18 is 3 squared times 2 to the first. So if I want to find the number of divisors, remember you look at your exponents of your prime factors, and you say, okay, 2 plus 1, so the exponent plus 1 more, times 1 plus 1, the exponent plus 1 more. So I have 3 times 2. Now I know that there are 6 divisors of 18. So if you break it down to the prime factors, and then look at their exponents, you always do the exponent plus 1, exponent plus 1, and then multiply. And that tells you how many divisors you have. It doesn't tell you what the divisors are, but it tells you how many you have. So this is what I have used to solve this, and I got to my answer pretty fast because I got a little bit lucky with my guessing. So for this one, I'm thinking, okay, I need 16 divisors. Now think of these numbers here. 3 times 2. So I'm thinking, okay, how can I get 16, but I don't want a perfect square number here. So I decided to try 4 times 2 times 2. Now what does that mean for my exponents up here? What it means is this number would be 3 plus 1, so I have something to the third power. This number would be 1 plus 1, so I have another number to the first power, and then this would be 1 plus 1, which is another number to the third power. Now I'm looking for the smallest number possible, so my thinking was this: what if I change this into 2 to the third? 2 to the third, so this is where I'm getting the 3. 3 plus 1 more tells me the number of divisors for that. So 2 to the third. And then I said, okay, what's my next smallest number for a factor? I tried 3. 3 to the first, because it's 3 to the 1, so 1 plus 1, that's the number of divisors. And then I did the next smallest, can't think of words right now. Next smallest number I could use, do that, I don't know, 5 to the first. So this is 8 times 3 times 5, 24 times 5, that's 120. Okay, so I'm thinking, let's try 120. It should have 16 divisors because we've got 3 plus 1, 1 plus 1, 1 plus 1. 4 times 2 times 2 should have 16 divisors. Let's prove it does. So our first divisors would be 1 and 120, then 2 and 60, then 3 and 40, then 4 and 30, then 5 and 24, then 6 and 20, 7 doesn't work, 8 and 15, 9 doesn't work, 10 and 12. 1, 2, 3, 4, 5, 6, 7, 8. So 16 divisors there. Okay, now I want to test this out to see if 3/4 of my divisors are positive. Let's just look at the negative numbers, not negative, the odd numbers. 1, 2, 3, 3, 4. 4 out of 16 are odd. That is 1/4, which means 3/4 of our numbers are even numbers. So I found my number. My number is 120. Now, if that wouldn't have worked, I would have tried something else. Maybe I would have done 3 plus 1 times 3 plus 1. So maybe after this, I would have tried 2 to the third times 3 to the third and see if I would have gotten 3/4 even divisors of this one. Because I got 4 times 4 right there, right? And it turns out, I checked it out, it doesn't give you 3/4. So anyways, 120 is our smallest number. I told you this one was brutal. I got lucky on that one because I guessed right at the beginning. Sometimes guessing just works in math counts. All right, next one. Let f of x equal 237 over 2x minus 7. What is the sum of all integer values of x such that f of x is also an integer? Okay, all the words to say this. This number needs to be able to go into this number evenly. We want to find all of the x values where if we plug it in, it'll come out to an integer value. So it has to go in there evenly. All right, so first thing I want to do is break down 237. So if I break down 237, 2 plus 3 plus 7 is 12. So 3 has to go in there. 3 goes in here 79 times. Those are the prime factors. So there are only 4 divisors. 1 in 237 and 3 in 79. There's my 4 divisors of 237. So 2x minus 37 could be 1, it could be 237, it could be 3, or it could be 79. But you have to think through the problem. It says integer values, so negatives are okay too. So then we could also use -1, 237, -3, and -79. This was my mistake the first time I did this. I only did the positive ones. So at this point, we know that the denominator can be any of these 8 numbers. So now I just have to plug in 2x minus 37 equals each of these numbers, equals 1, equals 3, equals 237. So basically, we're going to just take all of these numbers, we're going to add 37, and then divide by 2. So if I add 37 and divide by 2 to this number, I end up with 19. Add 37, I get 38. Divide by 2, I get 19. So 19 is one of my numbers. To this one, I add 37 and get 274. Divide by 2, and I get 137. Add 37 to this number, I get 40. Divide by 2, I get 20. Add 37 to this number, I get 116. Divide by 2, that's 58. Add 37 to this number, I get 36. Divide by 2, I get 18. Add 37 to, that's a negative. Add 37 to this one, I get 200, negative 200. Divide by 2, and I get negative 100. This one, add 37 to it, I get 34. Divide by 17. By 2, I get 17. Talking and mathing is hard. Next one, I add 37 to this one, I get negative 21. No, I get negative 42. Divide by 2, negative 21. All right, these are the 8 numbers that we get. These are the 8 possible values of x. I add them all together, and what did I get earlier? I got 148. I think that is the right answer. 99% sure that's right. Next, each positive integer, 1 to 100 inclusive, is divided by 17. What is the sum of all 100 remainders? Okay. So I'm going to go ahead and if I take 1 and divide by 17, the remainder is 1. If I do 2 divided by 17, the remainder is 2. All right, if I keep on doing that, 1 through 16 will give us, well, 1 through 17. So the numbers 1 through the number 17 will give us a remainder of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And then when we get to 17, we'd have a remainder of 0. So this is all the numbers from 1 to 16. And then when we get to 17, we got 0. That process is going to keep on repeating every 17 numbers. So all the numbers, if we add them from 1 to 16, we can find the value of that. So when you want to add a bunch of numbers together, remember the formula is n times n plus 1 divided by 2. So if I want to add the first 16 numbers, n is 16, so I would do 16 times 1 more than 16, which is 17, and then divide by 2. And 8 times 17, because I'm dividing by 2 right here, 8 times 17 ends up being 136. So every 17 numbers, I should get 136. All right? So how many times am I going to get 17 numbers? Well, 17, the first 17 numbers, I get 136. When I get to 34, because that's the next 17, I would get another 136. The next 17 would be 51. And I would get another 136. The next 17 would put me at 68. And that would be another 136 remainders. Add 17 to this one. That puts me at 85. And that's another 136. Add 17 gets me up to 102. So that's another 136. Problem is, I went 2 over. Now remember, the last number has a remainder of 0, which means the number right before it has a remainder of 16. So I used 2 too many numbers. Well, the 102, not too bad because that gives me a 0, but 101 would give me a remainder of 16. So I need to subtract out 16 because I went too far on this one. So it's basically 1, 2, 3, 4, 5, 6, 136 times 6 minus 16, and that comes out to an even 800. All right, almost done. Ooh, this has been a long one. It's almost 30 minutes. My goodness. A right triangle has a 30-degree interior angle and an interior length for its shortest side, and an interior length for its shortest side. Oh, integer. Misreading. It has a right triangle, has a 30-degree interior angle, and an integer length for its shortest side. The side lengths of this triangle have a product whose square is s. What is the sum of the possible values of s that are at most 20, 25? So if you did math counts last year, hopefully you learned in math counts that 2025 was a perfect square year. This was 45 squared. We can use this here. I'm not going to, but some people use the 45 squared for that. So we've got a right triangle. So on problem number 154, I showed you the special right triangle formula for a 45, 45, 90. Now this one is a 30, 60, 90 triangle. I do have a video somewhere in the math counts thing about the special right triangles. Maybe I'll post it to Google Classroom so you guys can look at it. But anyways, in the 30, 60, 90 triangle, this is half of an equilateral triangle. This side would be B. This is the shortest side. The hypotenuse would be double that. And the medium-sized leg, or the larger leg over here, would be B times the square root of 3. Okay, so our shortest side is B. Our second shortest side is b root 3, and our longest side is 2 times b. Now it says that the shortest side has an integer length, and we want to know the sum of all the possible values of s. S is the square of all of these multiplied together. So we're going to multiply all these, the product of the three sides. So here's the product. And then we're going to square that number. So what is the sum of the possible values of s? So I want to know the possible square values here. So the first integer value I could use is 1, which would make this side 1 root 3, or just root 3, which would make this side 2 times 1, 2. So the product here is going to be 2 root 3. Now if I square this, 2 times 2 is 4, and then root 3 times root 3 is 3, so the square would be 12. That is under 2025, so I can use that number right there. Next one, I would say the integer value of this one is 2. That would make this one 2 root 3, which would make this 2 times 2, 4. So 2 times 2 is 4, times 4 is 16. So I get 16 root 3. 16 times 16 is 256. Root 3 times root 3 is 3. 256 times 3 is, I wrote it down somewhere where I read it, 768. All right, now let's try 3. If the smallest side is 3, the middle one is 3 root 3, the longest side is twice that, which would be 6. 3 times 3 is 9, 9 times 6 is 54, and then root 3. All right, now this is where I think we tap out. 54 squared is 2,169. That is more than 2,025. So the only two that work were these two. And we're looking for the sum of the possible values of s. So that would be 12 and 768, which comes out to 780. Oh. Told you guys this one was brutal. I was not lying. Justin has an unlimited supply of dimes and quarters. How many different combinations of these coins can he pay exactly $5 for his board games? Okay, so he's got dimes and quarters. So I'm just going to look at the quarters. So he's got quarters and dimes. He can use 0 quarters and he'd have a whole bunch of dimes. Would we have 50 dimes? So that's the first one. Now he can't use 1 quarter because that's going to leave him. It's not going to give him an even amount that we can use. So he has to use an even number of quarters. So he could use 2 quarters. That would work. He could use, and then we'd have some number of dimes. I'm not even going to worry about that. Let's just look at the amount of quarters that he would need. So 0 quarters, 2 quarters, 4 quarters, 6, 8, 10. 10 quarters would end up being half the money, right? 10 quarters is $2.50. Yeah, it is. And then we could use 12 quarters, 14 quarters, 16 quarters, 18 quarters, and 20 quarters. And once we get to 20 quarters, there would be no dimes because 20 quarters is $5. So these are the number of combinations. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All we needed to do is focus on the quarters, not on the dimes. The quarters had a limiting factor of we can only use an even number of them, so we are done there. All right, last one. What is the least positive perfect square that is a multiple of 24? I don't need this. So let's just break down 24. 24 is 2 times 12. 12 is 2 times 6. 6 is 2 times 3. The prime factorization of 24 is 2 to the third power times 3 to the first power. Now, if we are looking for the least positive perfect square that's a multiple of this number, then I need to ask myself, what do I need to do to this to make it into a perfect square? Well, these two are not perfect squares because we don't have an even exponent. So I would need another 2. Another 2. And that would make that 2 to the 4th. And I would need another 3 because that would make that 3 to the 2nd. So this is the smallest perfect square where 24 goes into it evenly. So 2 to the 4th is 16, 3 to the 2nd is 9, 16 times 9, 144. 144 is the smallest perfect square that 24 would go into. Oh my gosh, 35 minutes, almost 36. All right, I warned you ahead of time. This is brutal. Have fun with math. It's great times. Bye-bye.